The morning of April 23, 1944, over the rail yards of Hamm, Germany, Captain Robert Johnson pulls his P-47 Thunderbolt into a shallow dive, the airframe shuddering under the weight of 2,000 pounds of bombs strapped beneath the wings. Behind him, 8 Browning 50 caliber machine guns, each loaded with 400 rounds, wait in their wing mounts. The radio crackles with broken German transmissions. Luftwaffe controllers are calling intercepts. Fokker-Wulf 190 pilots climbing fast from the east. Johnson glances at his fuel gauge, calculates the math in his head, and knows the truth that German intelligence still refuses to believe. The Americans have built a fighter that carries more ordnance than most light bombers, flies higher than most interceptors, and still has enough fuel to make it home across 300 miles of occupied Europe. This was not supposed to be possible. German engineering doctrine, refined through years of aerial combat over Spain and Poland and France, held that fighters must be light, agile, and specialized. You built an interceptor to kill bombers. You built a ground attack plane to destroy tanks. You did not combine them. The laws of physics, the Luftwaffe's technical staff believed, simply would not allow it. A heavy fighter laden with bombs would be a sitting target for any competent pilot in a nimble 109 or 190. Yet here they were, spring of 1944, and the reports flooding into Luftwaffe intelligence offices told a different story. American Thunderbolts were not just escorting bombers anymore. They were obliterating rail lines, strafing airfields, destroying convoys, and when challenged in the air, they were winning. The cognitive dissonance was profound. How could a single aircraft, weighing nearly 8 tons fully loaded, outfight and outlast purpose-built German fighters? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand what the P-47 Thunderbolt represented, you must first understand what it was not. It was not elegant. When the first prototypes rolled out of Republic Aviation's factory in Farmingdale, Long Island, in 1941, even American test pilots laughed. The fuselage was barrel-shaped, almost comically wide, housing the enormous Pratt & Whitney R 2800 double-wasp radial engine. 18 cylinders arranged in 2 rows, producing over 2,000 horsepower. The aircraft weighed 7 tons empty. Fully loaded with fuel, ammunition, and ordnance, it could exceed 15,000 pounds. For comparison, the British Supermarine Spitfire, the gold standard of fighter design at the time, weighed less than 6,000 pounds fully loaded. The German Messerschmitt Bf 109 weighed just over 7,000. The Thunderbolt was a different species entirely. Alexander Kartveli, the Georgian-born engineer who designed it, was not trying to build a dogfighter. He was trying to build a survivor. Kartveli had watched the early air battles over Europe with a cold, analytical eye. He saw that most fighters were shot down not in turning engagements, but in ambushes. A pilot who never saw his attacker had no chance, no matter how agile his aircraft. Kartveli's philosophy was simple. Give the pilot armor, give him an engine that could absorb punishment, give him altitude performance so he could see the enemy first, and give him enough firepower to end a fight in a single pass. The result was an aircraft that violated every conventional principle of fighter design and yet worked brilliantly because it ignored the wrong principles. The heart of the Thunderbolt's capability was not its guns or its bomb racks. It was the turbo supercharger system. This was not a simple bolt-on modification. It was an engineering marvel, a labyrinth of ducting that ran the entire length of the fuselage, channeling exhaust gases from the engine to spin a turbine that compressed incoming air, forcing it into the cylinders at high altitude, where the atmosphere was thin. This system allowed the R 2800 engine to produce full power at 25,000 feet, an altitude where most other fighters gasped for air. German pilots, accustomed to the superior high-altitude performance of their own aircraft, were stunned to discover that the Thunderbolt could not only reach their altitude, but could accelerate and climb while doing so. It rewrote the tactical calculations of air combat. But the supercharger was also the reason the Thunderbolt was so large. The ducting alone weighed hundreds of pounds. The system was temperamental, prone to overheating, and required constant maintenance. Early models suffered chronic failures. Pilots returning from missions over France in the spring of 1943 reported turbo failures at rates exceeding 15%. Republic's engineers worked around the clock, redesigning exhaust manifolds, improving seals, rerouting coolant lines. By late 1943, the system was reliable, and once it was reliable, the Thunderbolt became nearly unstoppable. The armament was equally uncompromising. 8 Browning M, 2 50-caliber machine guns, 4 in each wing. Each gun fired at a rate of 800 rounds per minute. A 2-second burst delivered over 200 rounds. The kinetic energy was devastating. 50-caliber rounds could punch through the engine block of a truck, shred the wing spar of a fighter, or ignite the fuel tanks of a locomotive. American pilots called it a flying buzzsaw. The guns were arranged in the wings, outboard of the propeller arc, which meant there was no synchronization gear to fail. They simply fired, all 8 at once, converging their fire at a point 300 yards ahead of the aircraft. Anything in that cone of fire disintegrated. The bomb load was the final piece. The P-47D, the most common variant, could carry 2,500 pounds of ordnance. Typically, this meant 2 1,000-pound bombs and a 500-pound bomb, or 3 500-pounders and a set of 5-inch high-velocity rockets. The bombs were mounted on underwing pylons and a centerline fuselage rack. The pylons were stressed to handle the weight and the aerodynamic loads of high-speed flight. Early tests revealed that dropping bombs at speeds above 400 miles per hour could cause the bombs to tumble and miss their targets by hundreds of yards. Republic engineers developed timed release mechanisms and stabilizing fins. By 1944, Thunderbolt pilots could dive at terminal velocity, release ordnance with precision, and pull out without exceeding the structural limits of the airframe. This combination, guns and bombs on a single platform, was revolutionary. Most air forces separated these roles. The Luftwaffe used Stukas for ground attack and 109s for air superiority. The Royal Air Force used Typhoons for ground attack and Spitfires for interception. The Americans, constrained by logistics and the vast distances of the European theatre, needed versatility. They needed an aircraft that could escort bombers deep into Germany, then peel off and strafe a rail yard on the way home. The Thunderbolt was that aircraft. But its versatility came at a cost. Fuel consumption. The R2800 engine, producing over 2,000 horsepower, burned fuel at a prodigious rate. At combat power, the Thunderbolt consumed nearly 150 gallons per hour. That gave it roughly 2.5 hours of flight time, enough to reach the German border from England, but not enough to escort bombers to Berlin. To extend its range, engineers developed external drop tanks. These were pressed steel or even paper and resin tanks, mounted under the fuselage or wings, holding an additional 100 to 200 gallons. The tanks were expendable. Once empty, pilots jettisoned them before entering combat. By mid-1944, with the introduction of the 108-gallon paper drop tank, the Thunderbolt's combat radius extended to nearly 500 miles. Suddenly, no target in occupied Europe was safe. The logistics of keeping the Thunderbolt flying were staggering. Each aircraft required constant maintenance. The R2800 engine, robust as it was, needed an overhaul every 200 hours of flight time. The supercharger ducting had to be inspected for cracks after every mission. The 50-caliber guns had to be cleaned, oiled, and test-fired. Ammunition belts had to be loaded by hand, each round checked for defects. Bombs had to be transported from depots, often under enemy fire, and mounted on the aircraft by ground crews working in freezing rain or blistering heat. The fuel, high-octane aviation gasoline, had to be filtered multiple times to prevent contamination. A single grain of sand in the fuel system could seize the engine at 20,000 feet. The men who maintained the Thunderbolts were largely invisible to history. They worked 18-hour shifts, slept under the wings, and lived in tents on muddy airstrips carved out of French farmland. Many were barely out of high school. They learned to rebuild engines with improvised tools, to patch bullet holes with sheet metal scavenged from wrecked aircraft, to keep the machines flying through sheer determination. One crew chief, interviewed decades later, said that he could tell the condition of an engine just by listening to it start. A healthy R2800 had a deep, rhythmic growl. A sick one coughed and sputtered. He said he never lost a pilot to mechanical failure, and he said it with the pride of a man who knew he had saved lives with his hands. The Thunderbolt entered combat over Europe in the spring of 1943. The 8th Air Force, stationed in England, was suffering catastrophic losses. Daylight bombing raids over Germany were being torn apart by Luftwaffe fighters. The bombers, B-17 Flying Fortresses and B-24 Liberators, flew in tight formations for mutual defense, but without fighter escort, they were slaughtered. The P-38 Lightning, the Americans' first long-range fighter, had the range but lacked the performance at high altitude. The P-51 Mustang, which would later become famous, was still in development. The Thunderbolt was rushed into service, and the early results were mixed. The first missions revealed the aircraft's weaknesses. It was heavy. In a turning fight at low altitude, a Focke-Wulf 190 could outturn it easily. It was slow to accelerate. If a pilot was caught at low speed and low altitude, he was dead. The early pilots, trained in the tactics of World War I dogfighting, tried to fight the Thunderbolt like a Spitfire. They lost. Badly. The kill-to-loss ratio in the first 3 months was barely 1-to-1. The aircraft was blamed. Pilots called it the Jug, short for Juggernaut, but the nickname was not affectionate. It was a resignation. They were flying a machine they did not yet understand. Then, the doctrine changed. A handful of pilots, men like Hub Zemke and Francis Gabreski and Robert Johnson, began to figure out how to fight in a Thunderbolt. The key was altitude. The Thunderbolt could climb to 30,000 feet and cruise there comfortably, higher than almost any German fighter could operate effectively. From that altitude, it could dive. And in a dive, the Thunderbolt was faster than anything in the sky. Pilots began using slashing attacks. Dive from above, fire a burst, keep diving, and extend away. Never turn. Never slow down. Use speed and altitude as weapons. The Germans called these tactics boom and zoom. The Americans called them winning. The transformation was rapid. By the summer of 1943, the Thunderbolt squadrons were racking up kills. The 56th Fighter Group, Zemke's Wolfpack, became legendary. They developed the Finger 4 formation, 4 aircraft flying in a staggered line, each pilot covering the others. They trained relentlessly, practicing high-speed gunnery and coordinated attacks. They studied the Luftwaffe's tactics, learned to anticipate the German fighters' moves, and exploited every weakness. By the end of 1943, the 56th Fighter Group had the highest kill ratio in the 8th Air Force. The Jug had become a legend, but air superiority was only half the mission. In early 1944, as the Allies prepared for the invasion of Normandy, the Thunderbolt was tasked with a new role: ground attack. The Luftwaffe was being bled white over Germany, but the Wehrmacht still controlled vast territories. Rail lines carried reinforcements, convoys moved supplies, airfields launched interceptors. The Allies needed to strangle German logistics, and the Thunderbolt was the perfect weapon. It could carry bombs. It could strafe with devastating firepower, and it could survive the intense anti-aircraft fire that surrounded every strategic target. The first large-scale ground attack missions began in March 1944 as part of Operation Strangle. The objective was to destroy the rail network in northern France and Belgium, cutting the flow of German reinforcements before D-Day. Thunderbolts flew hundreds of sorties daily, bombing rail yards, strafing locomotives, and cratering tracks. The results were immediate. German logistics collapsed, fuel shipments stopped, ammunition convoys burned. Entire divisions were stranded without supplies. The Wehrmacht's field commanders sent frantic reports to Berlin, describing relentless attacks by American fighter bombers that appeared without warning, struck with precision, and vanished before interceptors could respond. The Luftwaffe tried to adapt. Anti-aircraft defences were reinforced. Flak batteries surrounded every rail yard and bridge. German intelligence officers pored over the wreckage, trying to understand how the Thunderbolts could carry so much ordnance and still fight. One captured Luftwaffe report, dated May 1944, describes the P-47 as an armoured ground attack aircraft with the performance of a high-altitude interceptor. The report concludes that such an aircraft should not be possible given known engineering constraints. The author speculates that the Americans have developed a new type of engine or have discovered a way to reduce weight without sacrificing strength. The truth, which the Germans never fully grasped, was simpler. The Americans had built the aircraft correctly from the start. On the morning of June 6, 1944, D-Day, the Thunderbolt proved its worth beyond any doubt. Over 2,000 sorties were flown in the first 24 hours. Thunderbolts bombed coastal defences, strafed German positions on the beaches, and destroyed reinforcements moving toward Normandy. The noise alone was overwhelming. Soldiers on the ground, both Allied and German, described the sky as a continuous roar of engines. One German officer, captured near Carentan, said that the Americans controlled the sky so completely that moving in daylight was suicide. He said his men dug foxholes and waited for darkness because the sound of a Thunderbolt's engine meant death was seconds away. The cost was heavy. Ground attack flying was the most dangerous mission in the air war. Pilots flew at low altitude, often below 1,000 feet, through walls of anti-aircraft fire. Tracer rounds arced up from every hedgerow. Machine guns rattled from farmhouses. Flak shells burst in black clouds, shredding wings and puncturing fuel tanks. Casualty rates among ground attack pilots exceeded 30% in some squadrons. Men flew 4 or 5 missions a day, came back with aircraft so damaged they should not have been able to fly, and took off again the next morning. The survival rate was brutal, but they kept flying because the alternative was unthinkable. Without air support, the invasion would fail. The technical reality of what the Thunderbolt could carry was staggering when examined in detail. A standard load for a ground attack mission in the summer of 1944 consisted of 2 1,000-pound general-purpose bombs mounted on underwing pylons, plus a centerline rack carrying either a 500-pound bomb or 6 5-inch high-velocity aircraft rockets. The rockets, designated HVAR, were a recent innovation. Each rocket weighed 140 pounds and carried a warhead equivalent to a 5-inch naval shell. They were unguided, fired in salvos, and devastatingly effective against tanks, bunkers, and buildings. A Thunderbolt configured for maximum anti-armor work could carry 10 HVARs, 5 under each wing, plus its full ammunition load of over 3,000 rounds of 50 caliber. The total ordnance weight approached 3,000 pounds. Add fuel, pilot, and the aircraft itself, and you had a machine weighing over 8 tons trying to get airborne from a muddy strip in Normandy. Takeoff was the most dangerous moment. Pilots had to calculate weight, runway length, temperature, and wind with precision. Too heavy, and the aircraft would not rotate. Too much throttle too soon, and the torque from the massive propeller would pull the aircraft into a ground loop. The R2800 engine delivered so much power that inexperienced pilots often lost control on takeoff, veering off the runway and collapsing the landing gear. Training manuals emphasized a smooth, gradual application of power. Experienced pilots described it as feeling the aircraft's willingness to fly. You could sense, through the control stick and the rudder pedals, the moment when the Thunderbolt transitioned from a 10,000-pound truck to an aircraft. That moment, when the wheels lifted and the weight transferred to the wings, was described by many as the most exhilarating sensation in aviation. Once, airborne, the heavily laden Thunderbolt climbed slowly. A clean fighter, without external stores, could reach 10,000 feet in under 5 minutes. A fully loaded bomber variant took twice as long. This made the climb-out vulnerable. Luftwaffe tactics evolved to exploit this. German fighters would loiter near known Allied airfields, waiting for the moment when the Thunderbolts were heavy and slow. Several aircraft were lost this way in the early months of 1944. The solution was escort. One flight of Thunderbolts, configured as clean fighters, would orbit above the field while the ground attack flights climbed out. Once the bombers reached altitude and jettisoned their drop tanks, they could defend themselves. But those first 10 minutes were tense. The bombing itself required skill that went far beyond simply releasing ordnance. Dive bombing from a fighter was not like dropping bombs from a B-17 at 20,000 feet. The Thunderbolt pilot had to identify the target, roll inverted, pull through into a near-vertical dive, acquire the target in his gun sight, adjust for wind and airspeed, release at the precise moment to ensure the bombs would hit, and then pull out of the dive without exceeding the structural limits of the airframe or blacking out from G-forces. The entire process, from roll-in to pull-out, took less than 20 seconds, and during those 20 seconds, the pilot was a stationary target for every anti-aircraft gun within range. The dive angle mattered. Too shallow and the bombs would skip or tumble. Too steep and the pilot risked not pulling out in time. The standard attack profile was a 60-degree dive, initiated from 8,000 to 10,000 feet, with release at 3,000 feet. This gave the bombs enough time to stabilize and impact accurately while giving the pilot enough altitude to recover. But actual combat was never standard. Targets moved, weather obscured visibility, flak forced deviations, pilots adapted in real time, adjusting angles and release points based on instinct and experience. The best pilots could place a 1,000-pound bomb within 50 feet of a target from a screaming dive through exploding flak. It was not luck. It was math, physics, and ice-cold nerves. The rockets added another layer of complexity. HVARs were ballistic. Once fired, they flew in a straight line, subject to gravity and wind. They had no guidance system. Accuracy depended entirely on the pilot's ability to point the aircraft at the target and fire at the correct range. The effective range was roughly 1,000 yards. Closer was better, but closer also meant more exposure to ground fire. Pilots described rocket attacks as a game of chicken. You dove toward the target, centered it in your gun sight, waited until you could see individual vehicles or gun emplacements, and then fired a salvo and pulled out hard. The rockets left a trail of white smoke, and German gunners learned to track that smoke back to the aircraft. More than one Thunderbolt was shot down seconds after releasing its rockets. The firepower of the 50 caliber guns was equally precise and equally brutal. Each gun was harmonized to converge at a specific range, usually 300 yards. At that range, all 8 guns fired into a space roughly 6 feet across. The bullets were armor-piercing incendiary rounds, designed to penetrate metal and ignite fuel. A 2-second burst delivered enough kinetic energy to destroy a locomotive, flip a truck, or saw the wing off a fighter. But the guns had to be used carefully. Ammunition was limited. 3,000 rounds sounds like a lot, but at a combined rate of fire exceeding 6,000 rounds per minute, a pilot could empty all 8 guns in 30 seconds of continuous firing. Discipline was essential. Short bursts, aimed fire, no spray and pray. Ground crews reloaded the guns by hand after every mission. Each belt of 50 caliber ammunition weighed over 60 pounds. Loading all 8 guns meant handling nearly 500 pounds of ammunition, threading it through feed mechanisms, checking for jams, and ensuring the belts fed smoothly. It was exhausting work, done in all weather, often under the threat of German air raids. The ground crews took pride in their speed. The fastest teams could rearm and refuel a Thunderbolt in under 20 minutes. That speed kept the aircraft in the air. On D-Day, some aircraft flew 5 missions in a single day, returning only long enough to refuel, rearm, and let the pilot grab a sandwich before launching again. The fuel situation was a constant calculation. Every pound of bombs and ammunition reduced the fuel load the aircraft could carry. Every minute of combat burned fuel at maximum rate. Pilots had to balance mission requirements against survival. Running out of fuel over occupied France meant bailing out or attempting a forced landing, both of which often ended in capture or death. The ferry tanks helped, but they were not a perfect solution. The paper tanks in particular were fragile. They leaked. They sometimes failed to feed properly, leaving the pilot with less fuel than expected. More than one Thunderbolt ditched in the English Channel because the drop tank malfunctioned. Yet despite all these challenges, the Thunderbolt succeeded. The statistics tell part of the story. Between D-Day and the end of the war, P-47 seconds flew over 546,000 combat sorties in the European theatre. They destroyed over 7,000 aircraft in the air and on the ground. They obliterated 86,000 railway cars, 9,000 locomotives, 6,000 armoured vehicles, and 68,000 trucks. They dropped over 132,000 tons of bombs. These are not estimates. These are documented, verified numbers compiled from mission reports, gun camera footage, and post-strike reconnaissance photographs. The scale of destruction was industrial, systematic, and relentless. But numbers do not capture the human experience. The pilots who flew the Thunderbolt in ground attack missions described it as the most intense form of combat they ever experienced. Air-to-air fighting had a certain abstraction. You fought at high altitude, against targets that were distant and impersonal. The ground attack was visceral. You saw the faces of the men you were killing. You saw the trucks explode, the soldiers dive for cover, the buildings collapse. You flew so low that you could read the markings on railway cars, and you knew that every person on the ground with a rifle or a machine gun was trying to kill you. The psychological toll was immense. Pilots flew multiple missions per day, day after day, for months. They watched friends shot down. They returned to base with aircraft so damaged that ground crews shook their heads in disbelief that the plane had stayed in the air. They lived with the knowledge that the next mission might be their last. Some coped by becoming fatalistic. Others developed superstitions, refusing to fly without a particular scarf or photo. Many simply shut down emotionally, completing missions with mechanical efficiency, saving their feelings for later or never. One pilot, interviewed in the 1980s, said that he remembered the sound more than anything. The sound of the R2800 engine at full throttle was so loud that it drowned out thought. You could not hear the radio, you could not hear the guns firing, you could not hear the flak exploding. You existed in a bubble of noise. Your entire focus narrowed to the gun sight and the target and the pull of G-forces as you hauled the stick back to avoid hitting the ground. He said that for years after the war, he would hear that sound in his dreams, and he would wake up in a cold sweat, convinced he was about to crash. The Germans, for their part, developed a grudging respect for the Thunderbolt. Luftwaffe pilots called it the Indiana, a reference to the American Indian head insignia that many Thunderbolt squadrons painted on their aircraft. In combat reports, German pilots described the Thunderbolt as nearly impossible to shoot down. One report, filed by a Focke-Wulf 190 pilot in August 1944, describes an engagement in which he fired over 200 cannon rounds into a Thunderbolt at close range. The Thunderbolt's engine continued running. The pilot did not bail out. The aircraft simply continued its dive, released its bombs on target, and climbed away. The German pilot concluded that the Thunderbolt must be constructed from some kind of advanced armor that his cannon shells could not penetrate. He was not entirely wrong. The Thunderbolt's durability was legendary. The airframe was massively overbuilt. The wing spars were solid steel. The fuselage structure could withstand G-loads that would have torn apart a lighter aircraft. The radial engine, with its 18 cylinders arranged in a circle, could lose multiple cylinders and still produce power. Liquid-cooled engines, like those used in the Mustang or the Messerschmitt, had a critical vulnerability. A single bullet in the coolant system and the engine would overheat and seize within minutes. The R2800 had no coolant. It was air-cooled. You could shoot holes through the engine cowling, shatter cylinders, and the engine would keep running, albeit rough and losing power. But running? The armor protection for the pilot was equally comprehensive. Behind the pilot's seat was a sheet of armor plate, 3/8 of an inch thick, angled to deflect rounds coming from behind. The windscreen was layered bulletproof glass, 2 inches thick. The cockpit floor had additional armor to protect against ground fire. A pilot sitting in a Thunderbolt cockpit was surrounded by over 200 pounds of steel and armored glass. This made the aircraft heavier, but it also made the pilot far more likely to survive being hit. The survival rate for Thunderbolt pilots, who were shot down or forced to crash land, was significantly higher than for pilots of other fighters. Many walked away from crashes that should have been fatal. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Robert Johnson's survival on June 26, 1943, became the most famous example of the Thunderbolt's resilience. Johnson, flying with the 61st Fighter Squadron, was escorting bombers over France when his flight was bounced by Focke-Wulf 190s. In the ensuing fight, Johnson became separated from his wingman and was attacked by a German ace, Oberleutnant Egon Meyer. Meyer closed to point-blank range and fired repeated bursts into Johnson's aircraft. The Thunderbolt absorbed over 200 hits. The canopy was shattered. The engine was hit multiple times. The tail was nearly severed. Johnson, wounded and unable to bail out because the canopy was jammed, managed to keep the aircraft flying. He dove for the deck, using the Thunderbolt's superior speed in a dive to escape, and flew the crippled aircraft back across the English Channel. He landed at his base, and when the ground crew examined the aircraft, they could not believe it had stayed in the air. Photographs of Johnson's Thunderbolt, tail number 230505, show a plane that looks like it flew through a storm of shrapnel. Johnson survived without serious injury. He credited the Thunderbolt's armor and construction. He flew combat missions for the rest of the war and ended with 27 confirmed kills. Stories like Johnson's circulated among both Allied and German pilots. For the Americans, they were proof that the Thunderbolt could bring you home. For the Germans, they were deeply unsettling. The psychological impact of fighting an enemy who seemed invulnerable was corrosive. German pilots, already outnumbered and outgunned, began to lose confidence. Morale reports from Luftwaffe units in late 1944 describe widespread fatigue, fear, and a sense of hopelessness. Pilots who survived encounters with Thunderbolts often refused to engage them again unless they had overwhelming numerical superiority. The aircraft had become more than a weapon. It had become a symbol of American material dominance. The industrial capacity behind the Thunderbolt was as important as the aircraft itself. Republic Aviation, at its peak, produced over 1 aircraft per hour. The Farmingdale plant in New York and the Evansville plant in Indiana operated around the clock, employing over 40,000 workers, many of them women. The production line was a marvel of efficiency. Wings were assembled in one section, fuselages in another, engines in a third. The components came together on a moving assembly line, and aircraft rolled out the doors fully assembled and ready for flight testing. From raw materials to finished aircraft took less than 30 days. This meant that losses could be replaced almost immediately. The Luftwaffe, by contrast, was struggling to produce even a few hundred fighters per month by late 1944. German factories were being bombed. Materials were scarce. Skilled labor was being conscripted into the infantry. The disparity in production was as decisive as any battle. The logistical tail supporting the Thunderbolt was equally impressive. Every aircraft required a constant flow of spare parts. Engines needed overhauls every 200 hours. Propellers needed to be replaced. Tires wore out from repeated landings on rough fields. Instruments failed. Radios malfunctioned. Maintaining a squadron of Thunderbolts required a small army of mechanics, armourers, instrument technicians, radio operators, and supply clerks. The U.S. Army Air Forces developed an entire infrastructure to support forward operations. Mobile maintenance units followed the advancing armies, setting up shop in captured towns and abandoned factories. Parts were flown in by C-47 transports. Fuel convoys operated day and night. The system was not perfect. There were shortages and delays, but it worked well enough to keep the Thunderbolts flying, and that was what mattered. The summer and fall of 1944 saw the Thunderbolt reach its apex as a ground attack weapon. The breakout from Normandy, the liberation of Paris, the advance toward the German border, all were supported by relentless air attacks. The Thunderbolts of the 9th Air Force, operating from forward airstrips in France and Belgium, flew close air support missions that redefined what air power could achieve. They worked in coordination with ground controllers, often forward observers riding in jeeps just behind the front lines. The controllers would identify targets, relay coordinates by radio, and within minutes, Thunderbolts would appear overhead, bombing and strafing with pinpoint accuracy. This level of coordination, now standard in modern warfare, was revolutionary in 1944. The German army, already reeling from defeats in Normandy and the Soviet advance in the east, found itself unable to maneuver. Moving in daylight invited immediate air attack. Convoys were destroyed. Supply dumps were bombed. Even individual vehicles were targeted. German soldiers took to moving only at night, hiding in forests and buildings during the day, paralyzed by the constant threat from above. The Wehrmacht's operational flexibility, which had been its greatest strength in the early years of the war, evaporated. The Allied advance accelerated not because of superior tactics or firepower on the ground, but because the Germans could not move fast enough to respond. The Thunderbolt had achieved what strategic bombing had failed to do. It had crippled the German military's ability to fight. By December 1944, as the weather turned cold and the front lines stabilized near the German border, the Luftwaffe attempted one final offensive. The Battle of the Bulge began on December 16th with a massive German counterattack through the Ardennes forest. For the first week, bad weather grounded Allied air power. The Germans advanced rapidly, overrunning American positions and threatening to break through to the coast. The situation was desperate. Then, on December 23rd, the weather cleared. The Thunderbolts returned in force. Over the next 10 days, the 9th Air Force flew over 11,000 sorties. Thunderbolts attacked German tank columns, destroying over 400 armored vehicles. They strafed supply convoys, cutting off fuel and ammunition. They bombed crossroads and bridges, isolating German units. The offensive collapsed. By early January 1945, the Germans were in full retreat, having lost men and equipment they could not replace. The Thunderbolt had, once again, proven decisive. General Eisenhower later wrote that air power had been the critical factor in stopping the German offensive. Without it, he said, the Bulge might have succeeded. The final months of the war saw the Thunderbolt operating in conditions that would have been unimaginable 2 years earlier. By February 1945, Allied forces had crossed the Rhine and were driving deep into Germany itself. The Luftwaffe, once the most formidable air force in the world, had been reduced to scattered remnants. Fuel shortages meant that even the few operational aircraft could barely fly. Experienced pilots were dead or captured. Replacements were boys with less than 50 hours of flight time, sent up in aircraft they barely knew how to control. The skies over Germany belonged entirely to the Allies, and the Thunderbolt ruled those skies with absolute authority. The missions changed in character. There were fewer air-to-air engagements. German fighters rarely appeared, and when they did, they were quickly overwhelmed. Instead, the Thunderbolts focused on what they did best: destruction of infrastructure. Rail yards, bridges, factories, communication centers, anything that kept the German war machine functioning became a target. The attacks were methodical and thorough. Intelligence officers would identify a target, reconnaissance aircraft would photograph it, and then waves of Thunderbolts would strike, often within hours. The German ability to repair damage could not keep pace with the rate of destruction. Bridges stayed down, rail lines remained severed. The industrial heart of the Reich simply stopped beating. The introduction of napalm in early 1945 added another dimension to the Thunderbolt's arsenal. Napalm, a jellied gasoline mixture, was loaded into droppable tanks and used against area targets like fuel depots, supply dumps, and troop concentrations. The effect was devastating. A single napalm strike could create a firestorm that consumed everything within hundreds of yards. Pilots described the sight as both horrifying and mesmerizing. The fuel ignited on impact, spreading liquid fire that clung to surfaces and burned at temperatures exceeding 2,000 degrees. Buildings melted, metal warped. The psychological impact on German troops was profound. Survivors of napalm attacks described a terror unlike anything they had experienced, even in the brutal fighting on the Eastern Front. Yet, even as the Thunderbolt demonstrated its overwhelming destructive power, questions about its future were already being asked. The jet age had arrived. The Messerschmitt Me-262, though produced in limited numbers and plagued by mechanical problems, had shown that piston engine fighters were obsolete. The Me-262 could fly 100 miles per hour faster than the Thunderbolt. It could climb faster, accelerate faster, and disengage at will. In the few engagements where Thunderbolts encountered 262s in the air, the results were mixed. The jet's speed made it nearly impossible to catch, but its poor maneuverability and limited ammunition meant it could rarely achieve decisive results. Most Me-262s were destroyed on the ground, caught during takeoff or landing when they were vulnerable. The future was clear. Jets would replace propeller-driven fighters. The R-2800 engine, magnificent as it was, represented the peak of piston engine technology. There was nowhere left to go. Republic Aviation recognized this and began developing jet fighters even before the war ended. But the Thunderbolt's legacy was secure. It had proven that versatility, durability, and firepower could be combined in a single airframe. The aircraft that followed, from the F-84 Thunderjet to the A-10 Warthog decades later, all carried forward the design philosophy that Alexander Kartveli had pioneered. Build it strong, build it simple, make it survivable. On May 8, 1945, the war in Europe ended. Thunderbolt squadrons, scattered across Germany, France, and Belgium, received the ceasefire order. Pilots who had flown multiple missions per day for months suddenly had nothing to do. The silence was strange. Many described a sense of disorientation, of not knowing what to do with themselves. Some took their aircraft up for joyrides, rolling and diving through the clear spring sky, celebrating their survival. Others simply sat in their cockpits, engines off, trying to process what they had been through. The statistics compiled after the war told a story of overwhelming success. The P-47 Thunderbolt had flown more combat sorties than any other American fighter in the European theater. It had destroyed more ground targets than any other aircraft. Its loss rate per sortie was among the lowest of any combat aircraft, a testament to its durability and the skill of its pilots. Over 15,000 Thunderbolts were built during the war. They served in every theater, from Europe to the Pacific to the China-Burma-India theater. Pilots in every service praised the aircraft. It brought them home. But beyond the numbers, the Thunderbolt represented something larger. It was proof that American industrial power, when fully mobilized, was unstoppable. The Germans had brilliant engineers, experienced pilots, and advanced technology, but they could not compete with an enemy that could produce 15 fighters for every one they built, that could replace losses overnight, that could field aircraft carrying twice the ordnance of anything in the Luftwaffe inventory. The Thunderbolt was not just a weapon. It was a statement, a declaration that the United States had the resources, the ingenuity, and the determination to overwhelm any opponent through sheer material superiority. The human cost, however, should not be forgotten. Thousands of Thunderbolt pilots died in combat. Ground attack flying, for all the aircraft's protection, was brutally dangerous. Many were shot down by anti-aircraft fire. Others died in accidents, misjudging a dive or running out of fuel over enemy territory. Some were captured and spent the remainder of the war in POW camps. Their sacrifice made victory possible. Without the air superiority that the Thunderbolt helped establish, the invasion of Europe would have been far more costly, perhaps impossible. Every bridge destroyed, every rail line severed, every convoy obliterated meant fewer German soldiers at the front, fewer tanks opposing Allied advances, fewer casualties among the infantry pushing into Germany. The pilots who survived carried memories that stayed with them for life. Decades after the war, veterans would gather at reunions, and the conversation would inevitably turn to the Thunderbolt. They would talk about the sound of the engine, the feel of the controls, the sight of tracer rounds arcing up through the darkness. They would remember friends who did not come home. They would describe missions with a precision that suggested the memories were still vivid, still immediate, and they would say, almost, universally, that the Thunderbolt saved their lives, that no matter how badly shot up the aircraft became, it brought them home. That trust, forged in combat, never faded. The aircraft itself largely disappeared after the war. Most were scrapped, cut up for aluminum. A few were sold to foreign air forces and served for years in places like South America and Southeast Asia. Some found their way into private hands and were restored to flying condition. Today, fewer than 50 Thunderbolts remain in existence. A handful still fly, maintained by museums and collectors who understand their historical significance. When one takes off, the sound of that massive radial engine is unmistakable, deep, powerful, authoritative. It is a sound that connects the present to the past, a reminder of a time when the fate of the world hung in the balance, and machines like the Thunderbolt helped tip the scales. The legacy of the P-47 extends beyond aviation history. It influenced the development of close air support doctrine, the integration of air and ground forces, and the design of multi-role combat aircraft. Modern fighter bombers, capable of both air superiority and ground attack missions, are the direct descendants of the Thunderbolt's design philosophy. The lessons learned from operating the aircraft, from logistics to maintenance to tactics, shaped how air forces around the world train and fight. The Thunderbolt was not just a weapon of World War II, it was a template for the future of air warfare. In the end, the story of the P-47 Thunderbolt, carrying 2,500 pounds of bombs and 850 caliber machine guns, is not just a story about technology, it is a story about the people who built it, maintained it, and flew it into combat. It is about the workers in Farmingdale and Evansville, who assembled the aircraft with care and precision. It is about the mechanics who kept them flying through brutal conditions. It is about the pilots who climbed into the cockpit, day after day, knowing that each mission might be their last, and flew anyway because the mission mattered. Their courage, their skill, and their sacrifice turned an improbable design into a legendary weapon. The Germans could not believe what the Thunderbolt could do. By the time they understood, it was too late. The war was already lost. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The story begins not with a single decision or a dramatic moment on the battlefield, but with a quiet miscalculation that would echo across continents and reshape the course of the Second World War. In the late 1930s, as tensions mounted in Europe and Asia, military planners in Berlin, Tokyo, and Rome conducted assessments of potential adversaries. They studied industrial capacity, examined production figures, and evaluated the military readiness of nations that might oppose their ambitions. Among these potential opponents was the United States of America, a nation that had remained largely isolationist, distant from the conflicts brewing in the Old World. The consensus among Axis strategists was clear and confident. America, they believed, was soft, unprepared, and incapable of transforming its peacetime economy into a war machine that could challenge the established military powers of Germany, Japan, and Italy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. They saw a nation focused on consumer goods, automobiles, and domestic comforts. They saw factories designed for civilian life, not military production. They laughed at the possibility that this distant democracy could ever pose a serious industrial threat to their carefully honed war apparatus. German intelligence reports from 1939 estimated that American aircraft production capacity stood at approximately 2,000 planes per year, a figure that seemed manageable, even trivial, compared to the Luftwaffe's own production. Japanese naval planners, confident in their carrier-based air power and the quality of their Zero fighters, dismissed American aviation as technologically backward and strategically irrelevant. Italian military theorists, focused on Mediterranean dominance, paid little attention to American capacity at all. Yet within this dismissal lay the seeds of one of history's most profound strategic errors. The question that would haunt Axis leadership for the remainder of the war was simple but devastating. How could they have been so catastrophically wrong? When the United States entered the war in December 1941, following the attack on Pearl Harbor, the response from American industry was neither immediate nor automatic. It required vision, coordination, and an unprecedented willingness to transform every aspect of civilian manufacturing into military production. President Franklin Roosevelt, in a speech to Congress in January 1942, set ambitious targets that many considered impossible. He called for the production of 60,000 aircraft in 1942 and 125,000 in 1943. These numbers were so far beyond existing capacity that some military planners questioned whether they were achievable. Donald Nelson, chairman of the War Production Board, faced the monumental task of coordinating this transformation across thousands of companies, millions of workers, and an economy that had never attempted anything on this scale. The challenge was immense. Aircraft manufacturing was not simply a matter of scaling up production lines. It required precision engineering, specialized materials, skilled labor, and coordination across thousands of suppliers. The learning curve was steep, and the timeline was urgent. Factories that had produced refrigerators, automobiles, and household appliances were suddenly tasked with creating fighters, bombers, and transport aircraft. The General Motors Corporation, which had built nearly 2 million cars in 1941, ceased automobile production entirely in February 1942 and converted its facilities to military manufacturing. The Fisher Body Division, which had produced car bodies, began manufacturing wings and fuselages for aircraft. The Oldsmobile plant in Lansing, Michigan, which had built luxury automobiles, was retooled to produce cannon shells and aircraft components. This transformation occurred across the nation, from the smallest machine shops to the largest industrial complexes. The federal government provided financial backing through cost-plus contracts that guaranteed manufacturers would not lose money on military production, removing the financial risk that might have deterred participation. Tax incentives encouraged rapid facility expansion, and government loans financed the construction of new factories. One of the most striking examples of this transformation was the Willow Run plant in Ypsilanti, Michigan, built by the Ford Motor Company, specifically to manufacture B-24 Liberator bombers. Construction began in April 1941, months before the United States entered the war, reflecting the Roosevelt administration's understanding that war was likely and preparation was essential. The plant itself was a marvel of engineering and industrial design. It stretched over 3 million square feet, making it the largest manufacturing facility under one roof anywhere in the world. The assembly line was more than a mile long, and the building was so vast that it created its own weather patterns inside, with clouds forming near the ceiling on humid days. Henry Ford, who had revolutionized automobile manufacturing with the assembly line in the 1910s and 20s, applied the same principles to aircraft production. Each B-24 was broken down into sub-assemblies that could be manufactured simultaneously and then brought together in a carefully choreographed sequence. The fuselage moved along the line on specially designed jigs and fixtures, with workers adding components at each station. Wings were assembled separately and then attached near the end of the line. Engines, produced at other Ford facilities, were installed in a dedicated section. The entire process was designed for maximum efficiency, with materials delivered to each workstation at precisely the moment they were needed. This just-in-time approach minimized storage requirements and reduced the time components spent waiting to be installed. At its peak in August 1944, Willow Run was producing one complete B-24 bomber every 63 minutes, a rate that would have been unthinkable just a few years earlier. Workers moved along the line with practiced efficiency, installing engines, riveting fuselages, and assembling wings with precision that ensured each aircraft met the rigorous standards required for combat. The plant operated 24 hours a day, 7 days a week, with 3 shifts of workers maintaining continuous production. By the time production ended in 1945, Willow Run had produced 8,685 B-24 bombers, representing more than half of all Liberators built during the war. The sheer scale of the operation was staggering, and it represented just one facility among dozens across the nation. Boeing plants in Seattle and Wichita produced B-17 Flying Fortresses and B-29 Superfortresses. Douglas aircraft facilities in Long Beach, Santa Monica, and Oklahoma City manufactured C-47 transports and other aircraft. Consolidated Aircraft in San Diego, North American Aviation in Kansas City, and Lockheed in Burbank all contributed to the massive production surge. Each of these facilities employed tens of thousands of workers and produced hundreds or thousands of aircraft. The coordination required to manage this distributed production network was itself a logistical achievement that demonstrated American organizational capacity. The workforce that powered this transformation was as remarkable as the machinery itself. With millions of men serving in the armed forces, American industry turned to a labor pool that had been largely untapped in previous decades. Women entered factories in unprecedented numbers, taking on roles that had traditionally been reserved for men. They operated heavy machinery, performed precision welding, and assembled complex aircraft components. The iconic image of Rosie the Riveter became a symbol of this mobilization, but behind the symbol were real women whose contributions were essential to the war effort. At the Boeing plant in Seattle, women made up over 40% of the workforce by 1943. They worked as riveters, assemblers, inspectors, and electricians. Many had never worked in manufacturing before the war. They came from offices, farms, and homes, drawn by patriotic duty, economic necessity, or both. Rose Will Monroe, who became one of the models for the Rosie the Riveter image, worked as a riveter on B-24 and B-29 bombers at the Willow Run plant. She was a widow with 2 young daughters, and she took the job to support her family. Her story was typical of thousands of women who entered the industrial workforce during the war. They faced skepticism and sometimes outright hostility from male workers who doubted their ability to perform physically demanding work. Yet they proved themselves capable and often excelled in roles that required manual dexterity and attention to detail. Supervisors noted that women were often more meticulous in their work, catching defects that might have been missed and ensuring that quality standards were maintained even as production quotas increased. Training programs were hastily organized to teach the skills required for aircraft assembly. The federal government funded vocational training schools that offered accelerated courses in welding, riveting, blueprint reading, and mechanical assembly. Experienced workers, many of whom were older men unable to serve in the military due to age or health issues, became instructors, passing on knowledge that had taken years to acquire. Classes ran morning, afternoon, and evening to accommodate the around-the-clock production schedules. Students practiced on scrap metal and obsolete aircraft parts until they achieved the level of proficiency required for production work. The speed at which this workforce was assembled and trained was itself a testament to American organizational capacity. In 1941, the aircraft industry employed approximately 200,000 workers. By 1943, that number had grown to over 2 million, a tenfold increase in just 2 years. This expansion required not just training but also housing, transportation, and support services for workers who had relocated from other parts of the country. Yet the transformation was not without challenges and growing pains. Aircraft production required materials that were in short supply, including aluminum, steel, copper, and rubber. Aluminum, which had replaced wood and fabric as the primary material for aircraft construction in the 1930s, was essential for building modern planes. It was lightweight, strong, and resistant to corrosion, making it ideal for aviation. However, aluminum production required enormous amounts of electricity, and the existing capacity was insufficient to meet wartime demand. The federal government financed the construction of new aluminum smelters, particularly in the Pacific Northwest, where hydroelectric power from dams on the Columbia River provided cheap electricity. By 1943, American aluminum production had tripled from pre-war levels, reaching over 2 million tons per year. This expansion was critical to maintaining aircraft production, as each bomber required several tons of aluminum, and even smaller fighters needed substantial quantities. Steel for engines, landing gear, and structural components came from mills in Pennsylvania, Ohio, and Illinois. These facilities, many of which dated to the late 19th century, were pushed to their limits, producing both steel for ships and tanks, as well as the specialized alloys required for aircraft. Copper, essential for electrical wiring and engine components, was in chronically short supply. The government appealed to citizens to donate copper items, and scrap drives collected pots, pans, and even decorative items to be melted down and repurposed. Rubber presented perhaps the most severe shortage. Japan's conquest of Southeast Asia in 1942 cut off access to natural rubber plantations in Malaya and the Dutch East Indies, which had supplied over 90% of America's rubber before the war. This shortage threatened not just aircraft production but the entire war effort, as rubber was essential for tires, seals, hoses, and countless other components. The government responded with a crash program to develop synthetic rubber. Chemists and engineers worked frantically to perfect production processes that could create artificial rubber from petroleum and other chemicals. Factories were built at breakneck speed, and by 1943, synthetic rubber production had reached levels sufficient to meet military needs. The fact that American industry could identify a critical shortage, develop a technological solution, and implement it on an industrial scale within 18 months demonstrated the depth of scientific and engineering capacity that the Axis had failed to anticipate. Each of these supply chains had to be managed, coordinated, and protected from disruption. The War Production Board established allocation systems that prioritized military needs over civilian consumption. Rationing programs limited civilian access to gasoline, rubber, and metal products. Scrap drives became a regular feature of home front life, with communities competing to collect the most material for recycling. The government instituted rationing programs that limited civilian consumption of everything from gasoline to sugar to shoes. Citizens received ration books with stamps that determined how much of scarce goods they could purchase. Meatless Tuesdays and victory gardens encouraged people to reduce their consumption and grow their own food. These measures were not universally popular, but they were accepted as necessary sacrifices for the war effort. The entire economy was reoriented toward a single goal: victory in the war. This mobilization extended beyond manufacturing to transportation, finance, and agriculture. The United States Maritime Commission oversaw the construction of merchant ships to transport materials and finished aircraft across the Atlantic and Pacific. The famous Liberty ships, mass-produced cargo vessels, were built at a rate that seemed impossible. The record for constructing a Liberty ship was set in November 1942, when the SS Robert E. Peary was assembled in just 4 days and 15.5 hours from keel laying to launch. Ports on both coasts operated around the clock, loading and unloading vessels with a speed and efficiency that was constantly being refined. Longshoremen worked in shifts to ensure that ships spent minimal time in port, reducing the vulnerability to submarine attack and maximizing the number of voyages each vessel could complete. Railways transported raw materials to factories and finished aircraft to ports and air bases. The rail network, which had been struggling financially during the Depression, suddenly became critical infrastructure. The government coordinated train schedules to prioritize military shipments, and railroad workers put in long hours to keep the system functioning. The financial cost of this mobilization was staggering. The federal government spent approximately $300 billion on the war effort between 1941 and 1945, a sum equivalent to roughly $4 trillion in today's money when adjusted for inflation. Much of this spending was financed through borrowing, with the government selling war bonds to citizens and institutions. The national debt increased from approximately $40 billion in 1941 to $260 billion by the end of the war. Yet this massive expenditure produced tangible results in the form of the largest military force ever assembled and an industrial capacity that dwarfed anything the world had seen. At the same time, engineers and designers worked to improve aircraft designs, incorporating lessons learned from combat operations. Early models were often flawed, suffering from mechanical failures, inadequate armor, or insufficient firepower. The P-39 Airacobra, which entered service in 1941, was initially deployed as a fighter, but proved disappointing in that role. Its performance at high altitudes was poor, and it was outclassed by German fighters over Europe. However, when transferred to the Soviet Union under Lend-Lease, it found a more suitable role in low-altitude ground attack missions and became one of the most successful fighters on the Eastern Front. Feedback from pilots and maintenance crews in Europe and the Pacific was relayed back to designers, who made modifications and improvements. Field modification kits were developed to address immediate problems, and changes were incorporated into new production aircraft as quickly as possible. This iterative process meant that American planes were not static. They evolved continuously throughout the war, adapting to the changing demands of combat. The P-51 Mustang exemplifies this evolutionary process. The Mustang was originally designed to meet a British requirement for a fighter in 1940. The initial versions, powered by Allison engines, had excellent performance at low and medium altitudes, but were disappointing at the high altitudes where bomber escort missions were fought over Europe. In 1942, engineers at North American Aviation and Rolls-Royce collaborated to install the Merlin engine, originally designed for the British Spitfire, into the Mustang airframe. The result was transformative. The Merlin-powered Mustang had exceptional performance at all altitudes, long range when equipped with drop tanks, and handling characteristics that pilots praised enthusiastically. By late 1943, P-51 Mustangs were escorting bombers deep into Germany, engaging Luftwaffe fighters on equal or better terms, and gradually achieving air superiority over Europe. The Mustang became arguably the finest fighter aircraft of the war, and over 15,000 were produced. Its development demonstrated the importance of international collaboration, as the marriage of American airframe design and British engine technology created a weapon system that neither country could have produced alone. The willingness to adopt foreign technology and combine it with domestic expertise was another advantage that more rigid Axis procurement systems struggled to match. German and Japanese designers often pursued perfection rather than practical effectiveness, producing aircraft that were technically impressive but difficult to manufacture in large numbers. The psychological impact of this production surge on Axis leadership cannot be overstated. In the early stages of the war, German and Japanese planners had counted on their ability to maintain qualitative and quantitative superiority in the air. Germany had pioneered the use of coordinated air power in its blitzkrieg campaigns in Poland, Norway, France, and the early stages of Operation Barbarossa. The Luftwaffe in 1940 was the most experienced and effective air force in the world, with pilots who had honed their skills in the Spanish Civil War and the opening campaigns of World War II. German aircraft, like the Messerschmitt Bf 109 fighter and the Junkers Ju 87 Stuka dive bomber, had become symbols of German military prowess. Japan had built a formidable naval air force that dominated the Pacific in the early months of the war. The Mitsubishi A6M0 fighter was superior to any Allied fighter in the Pacific theater in late 1941 and early 1942, with better maneuverability, longer range, and experienced pilots who had been fighting in China since 1937. Both nations had invested heavily in aircraft development and production, and both believed that their technological edge and industrial capacity would be sufficient to sustain their military objectives. German planners estimated that they could produce approximately 15,000 aircraft per year, a figure they considered adequate given their qualitative advantages and the assumption that the war would be won quickly through decisive campaigns. Japanese planners, constrained by a smaller industrial base, focused on quality over quantity, producing aircraft that emphasized performance characteristics like range and agility over survivability features, like armor and self-sealing fuel tanks. The appearance of American aircraft in large numbers shattered these assumptions. Intelligence reports filtering back to Berlin and Tokyo documented an industrial output that defied their initial estimates. German commanders, who had relied on precise calculations of enemy production capacity, found their projections invalidated by the relentless flow of American planes. Luftwaffe reconnaissance flights over North Africa in 1943 photographed Allied airfields, crowded with aircraft in numbers that seemed impossible. German intelligence officers initially suspected the photographs showed dummy planes intended to deceive them, but interrogations of captured Allied pilots confirmed that the aircraft were real and operational. By mid-1943, Luftwaffe fighter units on the Western Front were reporting encounters with American bomber formations that numbered hundreds of aircraft, escorted by growing numbers of fighters. The scale of these operations was unprecedented. A single raid might involve 600 or more bombers, each carrying several tons of explosives, supported by an equal number of escort fighters. German fighter pilots, even the experienced aces who had survived years of combat, found themselves overwhelmed by sheer numbers. They could shoot down individual bombers, but the formations kept coming, and American fighters increasingly dominated the skies. Japanese strategists, already stretched thin across the vast Pacific theater, faced an adversary whose resources seemed limitless. The realization that the United States could not only match but vastly exceed Axis production created a strategic dilemma that had no easy solution. In October 1943, Admiral Isoroku Yamamoto, the architect of the Pearl Harbor attack, was quoted in captured Japanese documents as acknowledging that Japan had awakened a sleeping giant. Though the authenticity of this specific quote has been debated by historians, the sentiment reflected a growing awareness among Japanese leadership that their initial victories had not crippled American capacity as hoped. Instead, they had provoked a response of overwhelming scale. Japanese war production, which had peaked at approximately 28,000 aircraft in 1944, could not keep pace with losses. Pilot training programs, which had produced highly skilled aviators before the war, were cut shorter and shorter as the need for replacements grew desperate. By 1944, Japanese pilots were entering combat with a fraction of the training hours that their predecessors had received. In Europe, the impact of American air power became increasingly evident as the war progressed into 1943 and 44. The combined bomber offensive, a joint effort between the United States Army Air Forces and the Royal Air Force, sought to cripple German industry and weaken the Nazi war machine through sustained strategic bombing. American doctrine emphasized precision daylight bombing, targeting specific time, industrial facilities, transportation networks, and military installations. The theory was that destroying key nodes in the German economy would have cascading effects that would cripple war production. The 8th Air Force, based in England, bore the primary responsibility for executing this strategy. B-17 Flying Fortresses and B-24 Liberators flew in massive formations, sometimes numbering 600 or more aircraft, to strike targets deep inside Germany. These missions were costly in the extreme. German air defences were formidable, combining radar-directed fighter interceptors with dense networks of anti-aircraft artillery. The Luftwaffe employed sophisticated tactics to break up bomber formations, including head-on attacks that targeted the cockpit and nose sections where defensive armament was lightest. German fighters were equipped with heavy cannon and rockets specifically designed to destroy bombers at long range, before defensive machine guns could effectively engage them. Flak, the German term for anti-aircraft fire, was concentrated around key industrial targets in such density that formations flying through it experienced devastating losses. A single mission could result in the loss of 50 or 60 bombers, each carrying a crew of 10 men. The human cost was staggering. In 1943, before long-range escort fighters became available, the average survival rate for a bomber crew completing the required 25 missions was less than 30%. Crews understood the odds they faced, and the psychological strain was immense. Yet the missions continued, and losses were replaced with new aircraft and new crews. The industrial capacity that allowed these losses to be absorbed and operations to continue was precisely what the Germans had failed to anticipate. In August 1943, the 8th Air Force launched a series of raids against German ball-bearing production facilities in Schweinfurt and aircraft factories in Regensburg. These raids, conducted without fighter escort for most of the route due to the extreme range involved, resulted in the loss of 60 bombers out of 376 dispatched, a loss rate of 16%. Such losses were unsustainable over the long term, yet the raids were repeated in October, with similarly catastrophic results. The second Schweinfurt raid lost 77 bombers, and an additional 122 were damaged so severely that they required extensive repairs. The 8th Air Force temporarily suspended deep penetration raids while it reassessed tactics and waited for long-range escort fighters to arrive in sufficient numbers. German leaders interpreted these losses as evidence that strategic bombing could be defeated through determined defense. They increased production of fighter aircraft, concentrating resources on defending the Reich rather than supporting ground operations on the Eastern and Mediterranean fronts. By early 1944, the Luftwaffe had over 1,000 single-engine fighters dedicated to the defense of Germany, a force that should have been more than adequate to inflict prohibitive losses on Allied bombers. Yet the equation changed with the arrival of the P-51 Mustang in numbers sufficient to provide escort throughout entire missions. Beginning in February 1944, American fighters accompanied bombers all the way to targets in Berlin and beyond, engaging German fighters and gradually achieving air superiority over Germany itself. The Mustang's combination of speed, maneuverability, and range made it arguably the best fighter of the war, and its impact on the air campaign was immediate and profound. German fighter losses mounted to unsustainable levels as American pilots, increasingly experienced and flying superior aircraft, destroyed the Luftwaffe in a war of attrition. During a single week in February 1944, known as Big Week, the 8th Air Force and 15th Air Force flew over 3,000 sorties against German aircraft production facilities and airfields. The raids destroyed substantial portions of German fighter production capacity and forced the Luftwaffe into massive air battles that resulted in the loss of over 400 German fighters and, more critically, experienced pilots who could not be replaced. The Luftwaffe never recovered from these losses. By the time of the D-Day landings in June 1944, Allied air superiority over Western Europe was absolute. German fighters were rarely seen over the invasion beaches, and Allied ground forces advanced with close air support that German troops could not match. The material reality of American production became viscerally apparent to German soldiers on the ground. Luftwaffe pilots who survived being shot down and German troops captured on various fronts reported their shock at the abundance of Allied equipment. Prisoners interrogated by American intelligence officers frequently commented on the quantity and quality of supplies available to Allied forces. German soldiers, who by 1944 were experiencing chronic shortages of fuel, ammunition, and even basic rations, found it demoralizing to confront an enemy who seemed to have limitless resources. American units had trucks, jeeps, and half-tracks in numbers that allowed rapid movement and supply. They had artillery ammunition sufficient for sustained barrages. They had close air support that could be called in with relative ease. The disparity was not just quantitative but psychological. German troops understood that they were fighting an enemy who could replace losses indefinitely while their own resources dwindled. In the Pacific theater, American aircraft played a different but equally critical role. The vast distances of the Pacific required planes that could operate over long ranges, often from remote island bases or aircraft carriers. The geography of the theater, consisting of thousands of islands scattered across millions of square miles of ocean, made logistics extraordinarily challenging. Transport planes like the C-47 Skytrain became the workhorses of the Allied logistics network, ferrying troops, supplies, and equipment across distances that would have been impossible to traverse by sea in the time available. The C-47, a military version of the Douglas DC-3 commercial airliner, was one of the unsung heroes of the war. It was not glamorous, and it did not receive the attention given to fighters and bombers, yet it was absolutely essential to Allied operations in every theatre. The C-47 could carry up to 6,000 pounds of cargo or 28 fully equipped troops. It could operate from primitive airstrips, land on rough terrain, and fly in adverse weather conditions. Its reliability was legendary. Maintenance crews appreciated its simple, rugged design that could be repaired in the field with minimal specialized equipment. Over 10,000 C-47s were produced during the war, and they served in roles ranging from troop transport to medical evacuation to supply delivery. In the China-Burma-India theatre, C-47s flew the Hump, the treacherous air route over the Himalayan mountains that supplied Chinese forces and American units operating in China. These flights were among the most dangerous of the war, with aircraft battling high altitude, severe weather, and Japanese fighters. Hundreds of planes and their crews were lost, flying the hump, yet the supply line remained open, demonstrating the willingness to accept losses to maintain strategic objectives. In the Pacific Island campaigns, C-47s delivered supplies to forward airstrips that had been carved out of jungle just days earlier. They evacuated wounded soldiers from combat zones, flying them to rear area hospitals where they received treatment that saved lives that would have been lost in previous wars. The speed with which wounded men could be evacuated from the front lines to surgical facilities was a major factor in the relatively low mortality rate among wounded American servicemen during World War II. Approximately 3% of American soldiers who received medical treatment died of their wounds, compared to 8% in World War I. This improvement was due in large part to rapid evacuation by aircraft and advances in medical treatment, but the aircraft made the medical advances operationally feasible. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, later stated that the C-47 was one of the 4 pieces of equipment most vital to Allied victory, alongside the bazooka, the jeep, and the atomic bomb. Fighters in the Pacific evolved to meet different requirements than those in Europe. Early in the war, American fighters like the P-40 Warhawk and the 4F Wildcat were outclassed by the Japanese Zero in most performance categories. The Zero was lighter, more maneuverable, and had longer range than any Allied fighter in late 1941. Japanese pilots, veterans of years of combat in China, used these advantages to devastating effect in the opening months of the Pacific War. Yet the Zero's advantages came with vulnerabilities. It lacked armor protection for the pilot and self-sealing fuel tanks, making it extremely vulnerable when hit. American pilots learned to exploit these weaknesses, developing tactics that emphasized teamwork, slashing attacks from altitude, and avoiding turning dogfights where the Zero's maneuverability gave it an advantage. The F-6F Hellcat, which entered service in 1943, was specifically designed to counter the Zero. It was heavier and less maneuverable, but faster in a dive, better protected, and armed with 650 caliber machine guns that could shred a Zero with a brief burst. Hellcat pilots developed tactics that played to their aircraft's strengths, using altitude and speed to dictate the terms of engagement. The results were dramatic. The Hellcat achieved a kill ratio of approximately 19-1 against Japanese aircraft, the best ratio of any American fighter in the war. Over 12,000 Hellcats were produced, and they destroyed more than 5,000 enemy aircraft in air-to-air combat. The availability of these aircraft in large numbers gave American carrier task forces air superiority wherever they operated, allowing the Navy to project power across the Pacific with minimal interference from Japanese air forces. The Battle of the Philippine Sea in June 1944 illustrated the cumulative impact of American aircraft production and training. Japanese naval aviation, once the most formidable in the Pacific, had been worn down by 2.5 years of sustained combat. The veteran pilots who had attacked Pearl Harbor and dominated the skies in the early campaigns were dead, and the training infrastructure to replace them had been systematically destroyed by American attacks on Japanese bases and oil facilities. By mid-1944, Japanese pilots entering combat had received minimal training, often fewer than 100 hours of flight time compared to the 300 or more hours that American pilots received. When the Japanese fleet attempted to challenge the American invasion of the Marianas, the result was catastrophic. American fighters, primarily F-6F Hellcats flying from aircraft carriers, intercepted Japanese attack planes in what American pilots later called the Great Marianas Turkey Shoot. Over the course of 2 days, June 19th and 20th, 1944, Japanese naval aviation lost approximately 600 aircraft and 3 aircraft carriers. American losses were minimal, with fewer than 30 aircraft lost in air combat. The lopsided nature of the battle was not the result of Japanese incompetence, but of structural realities. American planes were better, American pilots were better trained, and there were simply more of them. The Japanese could not replace their losses at a rate sufficient to maintain operational capability. The Americans could, and did, replacing losses within days and continuing operations without pause. The battle effectively destroyed Japanese carrier aviation as an effective force. Subsequent operations in the Philippines and at Okinawa saw Japanese aircraft employed primarily in kamikaze attacks, a tactic born of desperation when conventional operations became impossible. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The human dimension of aircraft production extended beyond factories and training bases to the communities that supported them. Entire towns sprang up around aircraft plants, hastily constructed to house the influx of workers. These communities were often chaotic, with inadequate infrastructure struggling to keep pace with rapid population growth. Willow Run, Michigan, experienced explosive growth as Ford built its massive bomber plant. Workers poured into the area from across the country, seeking employment and the opportunity to contribute to the war effort. Housing was in desperately short supply. Trailer parks and temporary housing projects were constructed, but demand far exceeded supply. Workers lived in converted barns, garages, and any structure that could provide shelter. Families doubled up in small apartments, and boarding houses rented beds in shifts to accommodate workers on different schedules. The strain on local services was immense. Schools were overcrowded, with classes running in multiple shifts to accommodate the children of war workers. Medical facilities were overwhelmed, and doctors worked long hours treating industrial injuries, infectious diseases spread by overcrowding, and the ordinary ailments of daily life. Local governments, designed to serve small communities, suddenly found themselves managing populations that had tripled or quadrupled in a matter of months. Roads were clogged with traffic as workers commuted to plants. Public transportation was inadequate, and companies organized car pools and chartered buses to get workers to their shifts on time. The challenges were enormous, yet these communities displayed remarkable resilience and adaptability. Neighbors helped one another navigate the difficulties of wartime life, sharing resources, information, and support. Churches, civic organizations, and labor unions provided social cohesion and organized activities that gave people a sense of normalcy amid the chaos. The shared sense of contributing to the war effort created bonds that transcended the hardships. People understood that their sacrifices, whether in the form of long work hours, cramped living conditions, or separation from family members serving overseas, were part of a larger national endeavor. This collective purpose sustained morale even as the war dragged on year after year. The factories themselves were microcosms of American society, bringing together people from diverse backgrounds and experiences. Southern blacks migrated north in large numbers during the war, seeking employment in defense industries and escaping the rigid segregation of the Jim Crow South. This great migration, which had begun during World War I, accelerated dramatically during World War II. African American workers took jobs in aircraft plants, shipyards, and steel mills, often facing discrimination and hostility from white workers and management. Segregation persisted in many defense plants, with separate facilities for black and white workers. Yet the acute labor shortage and the need to maximize production gradually broke down some barriers. By 1944, black workers were employed throughout the defense industry, though they often faced assignment to the least desirable jobs and limited opportunities for advancement. The experience of working in integrated or semi-integrated environments, earning decent wages, and contributing to a cause that was presented as a fight for freedom and democracy created expectations that would fuel the civil rights movement in the post-war years. Mexican-American workers, many recruited through the Bracero program that brought agricultural workers from Mexico, also contributed to war production. Women of all backgrounds entered the workforce, challenging gender norms and demonstrating capabilities that had been dismissed or ignored in peacetime. The war created opportunities for social mobility and experiences that would have lasting effects on American society long after the fighting ended. The evolution of specific aircraft types during the war illustrates the continuous improvement that characterized American production. The B-29 Superfortress represents perhaps the most ambitious aircraft development program of the war. Conceived in 1938 as a very long-range heavy bomber, the B-29 pushed the boundaries of contemporary aviation technology in every respect. It was designed to fly higher, faster, and farther than any previous bomber, carrying a heavy bomb load over distances that would allow it to strike Japan from bases in China and later the Marianas. The development process was plagued with problems from the beginning. The engines, Wright R-3350 duplex Cyclones, were the most powerful radial engines ever built, but they were prone to catastrophic overheating and fires. The pressurized cabin, necessary to allow the crew to function at high altitudes without oxygen masks, was difficult to seal properly and experienced leaks that endangered the crew. The remote-controlled defensive gun system, an innovation that allowed gunners to aim and fire turrets from sighting stations inside the pressurized cabin, was complex and unreliable. The aircraft's weight, at 120,000 pounds fully loaded, was far beyond anything previously attempted. Test flights revealed flaw after flaw. Engines caught fire with alarming frequency, killing test crews and destroying prototypes. The landing gear, stressed beyond its design limits, collapsed on rough runways. The complex electrical and hydraulic systems failed regularly. There were moments when it seemed the entire program might be abandoned as too ambitious, too complex, and too expensive. The cost of developing and producing the B-29 exceeded the cost of the Manhattan Project that developed the atomic bomb, making it the single most expensive weapons program of the war. Yet the engineers persisted, driven by the knowledge that the B-29 represented the only realistic means of bringing sustained air pressure to bear on Japan without an enormously costly invasion. General Henry Hap Arnold, commanding general of the Army Air Forces, staked his reputation on the program, pushing it forward despite the setbacks. Engineers at Boeing and Wright worked around the clock to solve the problems. Improved engine cooling systems reduced the overheating. Redesigned control surfaces improved handling characteristics. Reliability was gradually improved through thousands of small modifications and refinements. By the time the B-29 entered combat operations in June 1944, it was the most advanced bomber in the world, capable of flying at 30,000 feet at speeds exceeding 350 miles per hour, with a range of over 3,000 miles. The first B-29 combat mission was flown from bases in India against targets in Bangkok, Thailand. The mission revealed ongoing problems, with several aircraft lost to mechanical failures rather than enemy action. Operations from China, which required supplies to be flown over the Himalayas, proved logistically unsustainable. The capture of the Mariana Islands, Saipan, Tinian, and Guam in summer 1944 provided bases from which B-29s could strike the Japanese home islands directly. The 20th Air Force, operating from the Marianas, began sustained bombing operations against Japan in November 1944. Early missions, conducted at high altitude using precision bombing techniques similar to those employed in Europe, achieved disappointing results. Japanese weather, with persistent cloud cover and high winds at altitude, made accurate bombing nearly impossible. General Curtis LeMay, who took command of the 20th Air Force in January 1945, made the controversial decision to switch tactics to low-altitude incendiary attacks against Japanese cities. These raids, conducted at night from altitudes of 5,000 to 8,000 feet, used incendiary bombs to create firestorms in densely populated urban areas. The raids were devastatingly effective and morally troubling. The firebombing of Tokyo on the night of March 9th to 10th, 1945, killed an estimated 100,000 civilians and destroyed 16 square miles of the city. Similar raids against other Japanese cities killed hundreds of thousands and left millions homeless. The strategic purpose was to destroy the cottage industries that produced components for Japanese military equipment, disrupt transportation, and break civilian morale. The human cost was immense, and the ethics of targeting civilian populations remained controversial long after the war ended. Yet from a purely military standpoint, the B-29 campaign achieved its objectives. Japanese war production already strained by shortages of raw materials and the destruction of merchant shipping, was further crippled. The psychological impact on Japanese civilians and military leaders was profound. The B-29 also played a role in mining Japanese waters, dropping acoustic and magnetic mines that further restricted shipping and isolated the home islands, and ultimately, it was B-29s that dropped the atomic bombs on Hiroshima and Nagasaki in August 1945, bringing the war to its final conclusion. The fact that the United States could develop, produce, and deploy such an advanced aircraft while simultaneously conducting operations in Europe, Africa, and across the Pacific demonstrated an industrial and technological capacity that the Axis had fundamentally misjudged. Over 3,000 B-29s were produced by the end of the war, and though they arrived too late to participate in the European campaign, they proved decisive in the Pacific. The willingness to invest billions of dollars and accept significant technical risks in pursuit of a weapon system that might fail exemplified the American approach to the war. Resources were abundant enough that multiple parallel programs could be pursued simultaneously. The coordination between aircraft production and other aspects of the war effort was essential to success. Aircraft required fuel, ammunition, spare parts, and maintenance infrastructure. Aviation gasoline, a highly refined fuel with specific octane ratings required for high-performance engines, was produced in vast quantities by American refineries. The petroleum industry, centered in Texas, Oklahoma, and California, expanded production to meet military demands while still providing sufficient fuel for civilian needs. Ammunition for aircraft weapons, from 50-caliber machine gun rounds to bombs ranging from 100 pounds to 10,000 pounds, was manufactured by ordnance plants across the country. The logistics of ensuring that the right ammunition was available at the right bases, in the right quantities, at the right time, required sophisticated coordination. Spare parts, numbering in the hundreds of thousands of individual items, had to be manufactured, catalogued, shipped, and inventoried at bases around the world. Airfields had to be constructed, often in remote or hostile locations, to support operations. The Seabees, the United States Navy's construction battalions, built airstrips on coral islands that had been uninhabited jungle just weeks earlier. Using bulldozers, graders, and coral fill dredged from lagoons, they created runways capable of handling heavy bombers in a matter of days. These airfields were often constructed while fighting was still ongoing nearby, and Seabee units frequently had to defend their work sites against Japanese attacks. The construction battalions worked with a speed and efficiency that amazed observers. Once completed, these airfields became critical nodes in the American advance across the Pacific, allowing land-based bombers to strike targets that had previously been beyond reach. The airfield on Tinian, one of the Marianas, became the busiest airport in the world during the final months of the war, with B-29s taking off and landing around the clock. Mechanics and ground crews maintained aircraft under difficult conditions, often working outdoors in extreme heat or cold, with limited facilities and improvised tools. Their work was absolutely essential to keeping aircraft operational. A fighter squadron might have 24 aircraft assigned, but at any given time, a substantial number would be undergoing maintenance or repairs. Keeping an adequate number of planes flyworthy required constant effort from skilled mechanics who diagnosed problems, replaced components, and tested systems to ensure reliability. In the Pacific especially, the corrosive effects of salt air, high humidity, and tropical heat created maintenance challenges that had not been anticipated. Engines required frequent overhauls, electrical systems corroded and failed, and structural components weakened. Ground crews developed field-expedient solutions, improvising repairs with whatever materials were available, and keeping aircraft flying through ingenuity and determination. The strategic bombing campaign against Germany has been the subject of intense debate among historians and military analysts for decades. Critics have questioned the effectiveness of bombing in achieving its stated objectives and have pointed to the immense cost in lives and resources. American bomber crews suffered casualty rates comparable to infantry units engaged in sustained ground combat. The 8th Air Force, which bore the brunt of the bombing campaign in Europe, suffered over 26,000 killed in action and nearly 20,000 wounded or captured. These figures represent approximately 1 in 4 airmen who served in the 8th Air Force, a casualty rate that exceeded that of most ground combat units. Individual bomber groups sometimes lost half their aircraft and crews in a single disastrous mission. The psychological toll on surviving crew members was severe. They watched friends and colleagues die in burning aircraft, saw planes explode in mid-air, and returned from missions knowing that their chances of surviving a full tour of duty were statistically poor. The destruction of German cities killed hundreds of thousands of civilians and raised profound moral questions about the conduct of the war. The firebombing of Dresden in February 1945, conducted primarily by British bombers but involving American forces, killed an estimated 25,000 people and destroyed one of Europe's most beautiful historic cities. The raid occurred when Germany's defeat was already certain, leading to accusations that it served no military purpose and constituted a war crime. Similar questions have been raised about the overall strategic bombing campaign. Did the destruction justify the cost? Could the resources devoted to bombing have been used more effectively in other ways? These are legitimate questions that deserve serious consideration. Yet, from a purely military standpoint, examining the campaign's effects on German war production and military capability, the bombing had significant impacts that extended beyond the physical destruction of factories and transportation networks. It forced Germany to divert enormous resources to air defense, including fighters, anti-aircraft guns, and personnel that could have been used on other fronts. By 1944, over 1 million Germans were employed in air defense roles, manning flak batteries, operating radar stations, and serving in fighter units. These personnel were unavailable for service on the Eastern Front, where the Wehrmacht was engaged in a desperate struggle against Soviet forces. Thousands of 88mm anti-aircraft guns, which were also highly effective anti-tank weapons, were tied down in Germany defending cities rather than supporting armoured units in Russia or France. The Luftwaffe was forced to concentrate fighter production and assign its best pilots to defend the homeland, weakening air support for ground operations. German industry, forced to disperse production facilities to protect them from bombing, lost efficiency. Transportation networks, subjected to systematic attacks, struggled to move raw materials, components, and finished goods. The attacks on synthetic fuel plants, which intensified in mid-1944, created critical shortages that crippled both the Luftwaffe and German armoured forces. By the final months of the war, German tanks and aircraft were often immobilized for lack of fuel, despite being mechanically operational. Perhaps most importantly, from a strategic perspective, the bombing demonstrated to German civilians and military leaders that the Reich could not protect its homeland. The Nazis had promised security and prosperity through military conquest. The reality by 1944 was burning cities, disrupted services, and the constant fear of air raids. This psychological impact, though difficult to quantify, undermined confidence in the Nazi regime's ability to win the war and contributed to the erosion of German morale. The bombing campaign tied down resources, disrupted production, created fuel shortages, and demonstrated the Reich's vulnerability. These were significant strategic achievements, though the moral and human costs remained deeply troubling. The development of long-range escort fighters was crucial to the success of the bombing campaign and provides another example of American industrial responsiveness to battlefield requirements. Early raids deep into Germany suffered catastrophic losses because bombers lacked fighter protection over enemy territory. Existing escort fighters like the P-47 Thunderbolt and the P-38 Lightning had insufficient range to accompany bombers all the way to distant targets and back. German fighters could attack bomber formations with relative impunity once escort fighters had to turn back, inflicting losses that threatened to make daylight bombing unsustainable. The introduction of external drop tanks, which carried additional fuel that could be jettisoned when empty, extended the range of escort fighters. The P-47, equipped with two 108-gallon drop tanks, could escort bombers much deeper into Germany than previously possible. Yet it was the P-51 Mustang, equipped with drop tanks and powered by the Merlin engine, that fundamentally changed the equation. Mustangs could escort bombers all the way to targets in Berlin, Breslau, and even further east, engaging German fighters throughout the mission. The Mustang's combination of speed, maneuverability, and range made it superior to German fighters in most combat situations. American pilots, increasingly experienced and confident, began actively seeking combat with German fighters rather than simply defending bombers. Fighter sweeps ahead of bomber formations engaged German fighters on the ground and in the air, destroying them before they could attack the bombers. By early 1944, the balance had shifted decisively. German fighter losses exceeded replacement capacity, and pilot quality deteriorated as experienced aviators were killed and replaced with inadequately trained recruits. The transition from defensive to offensive fighter operations exemplified American tactical flexibility. Initially, escort fighters stayed close to bomber formations, reacting to German attacks. As the number and quality of escort fighters improved, tactics evolved to allow fighters more freedom to engage enemy aircraft aggressively. Fighter groups were assigned specific roles within the escort, with some remaining close to bombers, while others ranged ahead or to the flanks, seeking to disrupt German attacks before they developed. Top-scoring American aces like Major George Preddy, Captain Don Gentile, and Colonel Francis Gabreski built their records flying Mustangs and Thunderbolts in escort missions over Europe. Their success was made possible by aircraft that were equal or superior to anything the Luftwaffe could field, and by training that prepared them thoroughly for combat. The combination of quantity and quality in American fighter forces overwhelmed German air defenses, despite the skill and determination of Luftwaffe pilots. In the Pacific, transport and reconnaissance aircraft played roles that were often overlooked but absolutely essential to operational success. The island-hopping campaigns that gradually pushed Japanese forces back toward their home islands depended on the ability to supply forward bases quickly and reliably. Transport aircraft delivered everything from ammunition and fuel to food and medical supplies. They carried mail, which was critical for morale, and evacuated sick and wounded personnel. They moved commanders and staff officers between bases for planning conferences. The flexibility and reliability of air transport allowed American forces to maintain operations across vast distances that would have been impossible to manage by sea alone. Cargo ships required weeks to travel from the United States to forward bases in the Pacific, and they were vulnerable to submarine attack. Aircraft could make the same journey in days and could operate regardless of sea conditions. Reconnaissance aircraft provided intelligence that shaped operational planning. Photo-reconnaissance variants of fighters and bombers flew high-altitude missions over enemy territory, photographing installations, troop concentrations, and shipping. These photographs were analyzed by intelligence specialists who identified targets, assessed damage from previous attacks, and tracked enemy movements. The intelligence gathered by reconnaissance aircraft was often more timely and detailed than information from other sources. In an era before satellite imagery, aerial reconnaissance was the primary means of visual intelligence gathering. The ability to photograph enemy positions at regular intervals allowed commanders to understand the battlefield situation and make informed decisions. Specialized aircraft like the 5 Lightning, a reconnaissance variant of the P-38 fighter, were designed specifically for this mission. Stripped of armament to save weight and equipped with high-resolution cameras, these planes flew fast and high to avoid interception, bringing back photographs that were processed and distributed within hours. The psychological warfare dimension of air power extended beyond the physical destruction of bombing to include leaflet drops and radio broadcasts. American aircraft dropped millions of leaflets over enemy territory, providing information about Allied victories, encouraging surrender, and attempting to undermine enemy morale. The effectiveness of these psychological operations is difficult to assess, but captured documents and prisoner interrogations suggested that they had some impact, particularly in the final stages of the war when German and Japanese soldiers were increasingly aware that defeat was inevitable. The sight and sound of Allied aircraft became a constant reminder of enemy strength. The distinctive sound of American engines, whether the throaty roar of a Pratt & Whitney radial in a Thunderbolt or the smooth hum of a Merlin in a Mustang, was recognizable to soldiers on the ground. For Allied troops, it was reassuring. For Axis troops, it was a source of anxiety and fear. The final year of the war saw American aircraft production reach its peak and then begin to decline as victory became increasingly certain. In 1944, the United States produced 96,000 aircraft, the highest annual total of the war. Factories operated at maximum capacity, and the entire system, from raw material extraction to final assembly, functioned with remarkable efficiency. Production in 1944 alone exceeded the total production of either Germany or Japan for the entire war. This astonishing output represented the culmination of 3 years of industrial mobilization, workforce training, and logistical coordination. Every aspect of the system had been refined and optimized to maximize production while maintaining quality standards. Yet by 1945, as Germany collapsed in the spring and Japan's situation became desperate in the summer, production began to slow. Contracts were cancelled as military planners determined that sufficient aircraft were available to complete the war. Factories began planning for reconversion to civilian production, and workers started to look toward the post-war future. The transition was not seamless. Many workers, particularly women, were laid off as returning servicemen reclaimed their jobs or entered the workforce. The social and economic disruptions of this transition would take years to resolve. Yet the fact that American industry could shift from maximum war production back toward peacetime operations, while the war was still ongoing, demonstrated a flexibility and planning capability that had been evident throughout the conflict. By the time Japan surrendered in August 1945, following the atomic bombings of Hiroshima and Nagasaki and the Soviet entry into the Pacific War, the United States had produced approximately 300,000 military aircraft. This figure included fighters, bombers, transports, reconnaissance planes, trainers, and various specialized types. It represented an industrial achievement without precedent in human history. To put this number in perspective, consider that Germany produced approximately 120,000 aircraft during the entire war from 1939 to 1945. Japan produced approximately 76,000. The Soviet Union, which also achieved impressive production totals, manufactured approximately 157,000 aircraft. Britain produced roughly 131,000. The combined Axis production was less than 200,000 aircraft over 6 years of war. The United States alone produced 300,000 in less than 4 years of active combat. This disparity represented not just industrial capacity, but also access to resources, organizational efficiency, technological innovation, and the ability to mobilize an entire society toward a common goal. The Axis powers had entered the war confident that their early advantages in training, equipment, and battlefield experience would be sufficient to achieve victory before American industrial might could be brought to bear. They had fundamentally miscalculated the speed at which America could mobilize, the scale at which it could produce, and the determination with which it would prosecute the war. The story of American aircraft production is also the story of the individuals whose labor and ingenuity made it possible. Engineers who designed aircraft that pushed the boundaries of technology, factory workers who assembled those aircraft with precision and care despite difficult conditions, pilots who flew them in combat, often at great personal risk, ground crews who maintained them under challenging circumstances, logisticians who coordinated the vast supply networks that kept aircraft operational. Each of these individuals contributed to a collective effort that was greater than any single person could have achieved alone. The sense of shared purpose that characterized the American home front during World War II was not universal or uncontested. There were labor disputes, racial tensions, and disagreements about priorities and strategies. Yet beneath these conflicts was a broad consensus that the war had to be won and that everyone had a role to play in achieving victory. This consensus sustained the enormous sacrifices required and enabled the mobilization that produced 300,000 aircraft. The legacy of this achievement extended far beyond the immediate victory in World War II. The industrial techniques developed during the war, particularly in mass production and quality control, influenced manufacturing practices for decades afterward. The aerospace industry that emerged from wartime aircraft production became a cornerstone of the American economy in the post-war period. The workers who gained skills and experience in aircraft factories carried that knowledge into new careers. The women who had entered the workforce in unprecedented numbers during the war, though many were forced out in the immediate post-war years, had demonstrated capabilities that could not be easily dismissed or forgotten. The experience of wartime mobilization shaped subsequent American military and economic policy. The concept of maintaining a large standing military and a defense industrial base capable of rapid expansion became central to Cold War strategy. The lessons learned about coordination between government, industry, and military in pursuit of common objectives influenced everything from the interstate highway system to the space program. The recognition that technological superiority and industrial capacity were as important as battlefield tactics shaped military planning and procurement. The Manhattan Project, which developed the atomic bomb, demonstrated that massive scientific and industrial resources could achieve objectives that seemed impossible. The same approach would be applied to developing jet aircraft, guided missiles, computers, and eventually landing humans on the moon. For the Axis powers, the realization of American industrial capacity came too late to change their strategic course. By the time German and Japanese leaders fully understood the scale of production they faced, their own situations had deteriorated beyond recovery. Germany, fighting a multi-front war against opponents with overwhelming material superiority, could not win a prolonged conflict regardless of tactical skill or individual heroism. Japan, isolated from resources and facing an enemy that could replace losses faster than they could be inflicted, was in an impossible position. The initial laughter and dismissal with which Axis planners had greeted American industrial capacity turned to desperation and ultimately to acceptance of defeat. The strategic error of underestimating American potential was compounded by the inability to adjust strategy once the error became apparent. Both Germany and Japan continued fighting long after any rational assessment would have concluded that victory was impossible, at enormous cost to their own populations and to the peoples they had conquered. The question of whether the war could have ended sooner, with less destruction and loss of life, remains one of the most difficult ethical and strategic questions of the conflict. The decision to continue fighting when defeat was inevitable prolonged suffering for millions. Yet the alternative, surrender or negotiated peace on terms that might have allowed Axis regimes to survive in some form, was unacceptable to Allied leadership who had committed to unconditional surrender. The industrial capacity that produced 300,000 aircraft gave the Allies the luxury of fighting until they could dictate terms completely. There was no need to accept a compromise peace or to halt operations before total victory was achieved. This removed any incentive for negotiation and ensured that the war would be fought to absolute conclusion. The human cost was immense. Millions died in the final year of the war, including Holocaust victims murdered even as Germany collapsed, civilians killed in bombing raids and ground combat, and soldiers on all sides who fell in battles that occurred after the outcome was no longer in doubt. The story of American aircraft production during World War II is ultimately a story about the relationship between industrial capacity, national will, and strategic outcomes. The Axis powers had assumed that early military advantages and superior training would be sufficient to win the war before American industry could reach full production. This assumption proved catastrophically wrong. The speed and scale at which the United States transformed its economy from peacetime to wartime production exceeded anything the Axis had anticipated or could match. The willingness of American society to accept the sacrifices and disruptions necessary for total mobilization demonstrated a national commitment that Axis leaders had not believed possible in a democracy. The organizational capacity to coordinate production across thousands of facilities, employ millions of workers, and deliver finished aircraft to battlefields around the world showcased logistical sophistication that few nations could replicate. The 300,000 aircraft were not just machines. Each represented countless hours of labor, tons of raw materials, gallons of fuel, and the coordinated effort of designers, manufacturers, transporters, and maintainers. Each carried the hopes of a nation committed to victory and the determination of individuals who understood their role in the larger effort. The pilots who flew these aircraft into combat, the crews who maintained them, and the workers who built them were all participants in an endeavor that shaped the outcome of the most destructive conflict in human history. The fact that the Axis powers laughed at American industrial capacity in the early years of the war, only to be overwhelmed by it as the conflict progressed, stands as a reminder that underestimating an opponent's potential is among the most dangerous errors a strategist can make. Wars are not won solely on the battlefield. They are won in factories, shipyards, training facilities, and the countless unglamorous places where the machinery of modern warfare is created and sustained. The American achievement in aircraft production during World War II demonstrated that when properly mobilized and directed, a free society with access to resources and driven by common purpose could accomplish feats that seemed impossible. The transformation from an isolationist nation focused on domestic concerns to a military and industrial superpower capable of projecting power globally occurred in less than 4 years. This transformation was not inevitable. It required leadership that recognized the threat and acted decisively. It required citizens willing to sacrifice and contribute. It required innovation and flexibility in responding to challenges. It required the coordination of government, industry, and military toward shared objectives. The fact that these elements came together at a critical moment in history prevented Axis victory and shaped the world that emerged from the war. The 300,000 aircraft were instruments of that achievement, tangible symbols of a capacity that the Axis had dismissed and ultimately could not defeat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.